All right, thank you everyone for joining us today. In this very extremely cold weather. Alec told me that this is the coldest weather he ever been with.
10 to 20-degree margin.
So, hopefully we're having fun with this one. So we reminded him, hey, we're cold this week, and so it's like putting everything he can where you travel. All right, so it's very nice to have Dr. Koppel with us today. Alex received his PhD in 2017 at the University of Pennsylvania. And after that, he has worked with ARL, Army Research Lab in Maryland for a couple of years, and Amazon for a year, and then now he's in JP Morgan Chase for AI research. So he has a number of paper awards, and he has also received a director's award in ARL. So his research has been in reinforcement learning, inference, Bayesian inference, as well as their applications in financial markets. All right, today Alex is going to talk about some sampling strategies for reinforcement learning. The floor is all yours. Thank you
for that kind introduction. Yeah, it's a bit of a contrarian when many New Yorkers are flying to Florida for it to go even colder. And yeah, it's a time when many researchers are going to LLMs. I'm trying to go harder into experimental design. We'll get into exactly why. Yeah, so let's first talk about reinforcement learning, which are probably the two most important words in the title. I just want to attribute all of my very hardworking collaborators on this project, which have spanned both previous and current result. Okay. By the way, that's the thing like in the pocket and just turn it on. Good enough. Okay, so reinforcement learning. Once upon a time, everyone was watching David Silver's reinforcement learning lecture slides from University College London for the before the DeepMind days. And this is taken from that. Basically, this is a mathematical framework for sequential decision making in the midst of uncertainty. You imagine if you had some autonomous agent that selects actions, the environment, sequentially reveals rewards, and it causes a transition to a new state or observation. Yeah, its applications are pretty widespread by now in continuous control and web personalization and recommender systems. So let's talk about like what are some of the state of the art like solvers for reinforcement learning look like when you actually like try to implement them in practice. So here is an example of a method called DeepQ learning or DeepQ networks. And the point is you take this algorithm and you run it for very, very many training epochs, and you track the average cumulative reward or the average reward per episode, and you sort of like watch that evolve over time. And the particular like mechanics of this algorithm are in essential. I just want to point out like on the x-axis, each training epoch is taking between 100 and 1,000 samples, so that makes the x-axis on the order of a million on the order of millions. And it's also very volatile. And the story is very similar if you look at like other model-free methods like policy gradient method and its proximal variance. If you implement these methods on some of the sort of like benchmark environments, you're going to see this kind of like highly volatile evolution of the cumulative return over as a function of like the number of state action reward tuples process or episodes. And sort of like either in the sort of policy gradient space or in the Q learning space, you see that like we have this x-axis on the order of millions for what we call like model-free reinforcement learning. Nonetheless, these methods tend to be the sort of like dominant paradigm for training reinforcement learning like algorithms or policies. And a policy is more or less just like a way that you have your autonomous agent like define a distribution over the actions it selects over time. I'll formalize that and sort of like how does that policy evolve with respect to training index. Okay, so the dominant paradigm is really, or let's say the dominant like practice right now is you have like volatility and training, and you need to train quite a lot in a simulator. And so, and then at the point it's like you have your converged policy, but it's only been tested in sim. So how to account for the sim to real gap, like either like during policy optimization or after deployment. So the key questions that we're going to try to resolve in this talk is like, if you train an RL policy in your simulator, like how should you think both about not only convergence of your policy itself, but also convergence of your like simulator? Like what is your, how should we be sure that our simulator is like well calibrated in some sense, or like is converged, so that like the policy that we've trained in the simulator is actually meaningful? I think like, so that's like the first question, but I want to, let's say, put forth like one host of possible methods based off of model-based reinforcement learning. And then I want to talk in a little bit more detail about how do people think about the sim to real gap as formalized through what's called offline reinforcement learning, which is where you don't have access to a simulator, you only have access to a historical collection of trajectories, and you need to use those somehow for policy optimization. And so in both of them, I want to say there's like a unifying theme of trying to move beyond just the variance. It's like a model, or it's like it's a statistic of uncertainty, because like what is represented in your value distribution state transition model is frequently like multimodal in practice. So the fact that variance is very commonly used to represent uncertainty in a lot of these reinforcement learning algorithms may be overly restrictive, or might be like implicitly like imposing some Gaussian or sub-Gaussian assumptions that that may not be appropriate for having any sort of like trust in the sort of like underlying like true transition model that you would like to train your policy in. Okay, good. So before I go ahead, are there any questions? Great. Okay, so I want to put forth model-based reinforcement learning as a sort of a paradigm for trying to bring together the question of like, has my reinforcement learning policy converged, as well as like, is my is the like simulator or like sort of like uncertainty representation about my environment well calibrated? And because I think model-based reinforcement learning like offers a very like interesting collection of convergence criteria that try to like merge these questions together. So let's go into what are like the quote like mechanics of how model-based or Bayesian reinforcement learning works. So basically, you come into the system making some prior about the environment, which is basically just like a distribution over states and future rewards. And every time you update those distributions based off of new data. So there are a lot of different ways to actually do this. You can try to track like belief models, both in a sort of like model-free or a model-based setting. And even within these, there are like further breakdowns. I just want to comment, like, you can take things like deep Q learning or policy gradient methods and like inject some belief models into the parameter space or the state space directly through things like ensembling or like Monte Carlo sampling of nearby states. And that's roughly what like the Bayesian like variants of like DDPG and DQ learning and so forth do. Roughly experimentally, they have the sample complexity requirements very comparable to their quote like vanilla or like frequentist counterparts. The only thing that like this buys you on top of them is like basically like confidence intervals around states and parameters. And so really because of that, they're still like roughly limited to like training in simulators due to this like I would call it like heavy exploration requirement, or like let's just call it more generically like data hunger. Now in contrast, do you directly like put a prior over like states and reward or value distributions and then like track distributions over them using kind of like maximum a posteriori updates with respect to parameterized families. There are a bunch of methods that kind of like come within this framework, and they like experimentally tend to be very simple, efficient in practice. And I think it's I think it's like a 2013 Dyson-Rock paper about how to use Gaussian processes and a sort of a interesting model predictive control framework with nonlinear transition dynamics. And they show very like good simple efficiency, at least experimentally, but there's very little theory for like, why is this a good idea? But in contrast, actually, if you break this literature down just a little bit further, and you try to kind of like put a bounding box on model-based reinforcement learning methods that are specifically around what's called like posterior sampling. For those methods, also known as constant sampling, these methods actually do have like a more kind of like rigorous notion of convergence criteria based off of something called Bayesian regret, which for the statisticians here is something like how close is your posterior at step t like concentrated to its like population posterior. And so so we're going to focus on methods based off of posterior sampling and how they can be extended to reinforcement learning, both because they allow us to measure things like convergence of your policy as well as like convergence of your underlying like transition model, at least under some hypothesis that the ground truth is contained in your prior belief. Yeah, but misspecified setting is I would say scope of future work. Okay, so let's take a little time to formalize the setting. So yeah, you have an MVP with a state space, an action space, reward, a true transition model. We're going to focus on the finite horizon setting. There's some upper bound on the reward. On this row is something called occupancy measure, which is a kind of a distribution over all future state action probabilities if you take but yeah, it's a technical thing. So the point is like a key quantity here is called the value function. And I just want to note the quote like Bayesian value function is a little bit different than the vanilla one, because you assume that actions are being selected according to some particular policy pi, but also that rewards are coming from a particular like parameterized family of transition models. And then you compute an expectation with respect to the prior to kind of like integrate out the effect of that uncertainty. So it's almost the same as your vanilla value function, and there's just like this additional aspect that like we're going to put like a parameterized like a parameterized transition model over this, and we compute an expectation with respect to that as well. And Bayesian regret is just basically saying like, what is the suboptimality of my value function if I followed some particular policy at step k as compared to the optimal one according to my current transition model or like parameterized family in the and then in the MDP, and then you compute expectation over that over the policy and that family of transition models. Okay. Yeah, okay, those are things I just said. Right, so I want to, yeah.
Quick question. So in the first value function, where are the expectations taken?
Yeah, so we are computing expectation over the space of like transition models within a parameterized family, as well as policies. And then, but you would say, oh, in that case, isn't it some sort of like posterior value function? And that would be true, but then there's like an additional quote, like outer expectation over the prior that like gets rid of that. Oh, yeah. Right. So yeah, now I just want to go through like what is posterior sampling or Thompson sampling in a reinforcement learning context, and like where does it work and where does it have limitations. Okay, so the way it works is you start with some prior over your reward and state transition models. You sample, let's say if it's step 0, you sample according to that prior. You'll collect a trajectory. Then for that trajectory, you'll have some ability to evaluate the value function, and you'll compute your like next action to just be like the argmax of that value function. Sorry, you'll compute your next posterior to be the argmax of that value function. This is only actually a tractable computation if you make some very specific simplifying assumptions about the parameterized family, aka like Gaussian. But in general, trying to do an argmax here could be complicated. Then you select the next action to be sampled according to your like policy distribution, observe the next reward and state. This kind of like accumulating like data set of the algorithm history of trajectories like expands, and then yeah, and then rinse repeat. So yeah, for suitable conditions on the parameterized family, these things can be efficiently represented as these updates can be implemented with like tracking of like means and variances. But those are only really doable for Gaussians. If you move beyond the Gaussian assumption, then basically you need to track like a full like history of trajectories to parameterize these distributions. And I would say there's like a lot of kind of like experimental analysis about how to like do that efficiently. But before we get into like how some more technical guts, I just want to say that like if you try to take these methods like posterior sampling in some continuous control environments like Sudoku, et cetera, and you compare them to some of the other like model-free methods like soft actor critic or DDPG and so forth, the red curve, which is representing posterior sampling, actually seems to achieve like much more sample efficiency, at least experimentally. And I think that is really related to the fact that it's like trying to like learn a model of the environment while it's doing policy optimization. So that's sort of bringing together the question of like representing like the state transition model and also the policy suboptimality itself. Okay, but as I mentioned, like unless you assume that the like value or like the reward distribution in the state transition model are unimodal sub-Gaussian, then you can actually like implement these updates very efficiently. So like how to resolve that. And so what we said is like, let's see if we can move beyond the Gaussian assumption to just do like the next most complicated thing, which is mixture family, or for example, mixture of Gaussians. And if you go for a mixture of Gaussians, then it's well known in like non-parametric statistics that like as the number of trajectories goes to infinity, so should the parameterization of the mixture family. So then the question is like, how can you like explicitly trade off Bayesian regret and the complexity of your posterior so that you can have both good performance on like tractable complexities. Like that's the kind of like first part of this talk. And it's gonna hinge yeah, let's skip that. I just want to get to what is the actual like guts of how this works. Because the point is you can leave posterior sampling roughly unchanged. The only thing you need to do is figure out if I have a Gaussian mixture model representing the distribution over, let's say, the distribution over next states and rewards, how can I allow this thing to only retain important points from the past? And in general, if you can't use what you would need to do is your convergence criterion is basically look at a metric over distributions. And so what's true is like, yeah, you could look at things like Wasserstein distance, Hellinger metric, total variation norm, et cetera. But in general, those are like not computable for general mixture families. However, under some like smoothness assumptions on the transition model, basically that it like let's say that it satisfies something called Stein's identity. I want to hold on, let's get to where I actually, yeah. The point is like if you had some way of representing your mixture over current time and you could evaluate how close it is to some sort of like unknown optimal posterior, like that like divergence or distribution would be like the right way to select the number of points, or like the right number of like mixture components, which you can think the mixture components are just your past data set trajectories. So like in general, like you can't actually compute this, but let's say for a certain class of models that satisfy some smoothness assumptions, basically that you have like access to what's called like the score function of the target distribution. In practice, this tends to like not be a required assumption. It's just works for the theory to make this metric computable. The point is like under that assumption, which is called Stein's identity, then the difference, then a certain thing called an integral probability metric difference between your distribution and this target distribution, this term becomes zero. And then all you really need to do is like be able to compute some statistic related to your current distribution, which is like measuring sort of like in an intuitive sense, like diversity or like distributional spread of your current model. And so that like intuitive notion of like diversity or intuitive spread is like formalized as something called like kernelized Stein discrepancy. And it's very interesting that it all, at the end of the day, this ends up just being like a weighted combination of your like past trajectory data with respect to something called the Stein kernel, which like has an explicit kind of like closed form expression in terms of this like score function. And that kind of sounds exotic, but for mixture families, it's actually like directly computable. So it like takes this thing that seems intractable, like this metric over distributions, and it squashes it down to like closed form evaluation in terms of this test statistic. So
Quick
yeah.
question. So P star here, I think I missed it. Is it the best fit mixture model?
It's actually the population posterior.
Oh, so it's the actual posterior. So
Yeah.
you're assuming in this Bayesian framework that
Yeah.
it exists in space, and so then it exists somewhere, and
Yeah.
so then you're trying to find out sort of. I get it.
Yeah, and we say that population posterior, let's just say like satisfy some smoothness conditions
Got it.
associated with Stein's identity. Let's just say like when the dust and rubble clears, it ends up being computable as this kernelized Stein discrepancy. So we didn't come up with this, by the way. This is from a 2016 paper about that was subsequently extended a lot in terms of the Markov chain Monte Carlo literature, which has gained like new relevance these days for diffusion modeling, but that's an aside comment. The point is, now let's go back to the algorithm just for a second. Then how do we actually have a statistical test for which trajectories to retain? Basically, at every time, rather than augmenting your current like algorithm history, kind of like ad infinitum and letting the complexity grow unbounded, you just say, well, let's just like test if like, can I pick any points out according to whether they're causing, some epsilon error in kernelized sign discrepancy. And if they're not, then I can keep throwing away points until I hit the boundary of this error neighborhood. And then my like sort of compressed distribution will always be epsilon away from my like dense one. That's sort of like the intuition. And there's like a quote like descent lemma in the paper showing that like your posterior continues to contract up to some like epsilon error, which eventually is sort of like a critical component of how we're able to, here's the result I was talking about. Okay, so the point is like if you do this if you look at like the metric of your over your series of posteriors with this kernelized sign discrepancy, which is really like the kind of the expected integral probability metric of your current distribution to the target under these conditions. And if you choose that epsilon carefully, then you can roughly show that this is going to like contract to the population posterior. So then like the point is you need to choose that epsilon very carefully, which we parameterize in the paper with these like power of alphas, so that you can have like an explicit trade-off between model complexity of your mixture family as compared with this Bayesian regret. And so like I would say this was like the first result to our knowledge that could like extend posterior families in sort of like continuous MDP setting from simple Gaussians to mixture families. And so that like allows you to have like a much richer representation of uncertainty in your environment. So that was work from a couple of years ago. And then the question is like, okay, if once you can do that, this is kind of like all abstract. Does it actually like allow you to solve these problems in a kind of like more sample efficient manner, and like have richer kind of like belief representations in practice? And so like that's what this blue curve is roughly showing is like if we take our kind of compressed one as compared to the yellow one, which is dense, that uses the normal like non-parametric thing of retaining everything from the past, then you can actually get quite a significant model complexity reduction as compared with it seems like essentially negligible degradation in regret or sort of cumulative return in practice. Yeah, here I should say we're not actually plotting regret, we're plotting cumulative return because we don't actually know what is the oracle optimal in these environments. Okay, right. That's good. So there's a couple of things I want to say now. The first is so we can efficiently represent mixture families now with this machinery in model-based RL. There are a couple questions I think actually related to Mingy's question on, I don't know, slide 3 or whatever, like what is the definition of like value function or Bayesian regret? And there actually like is an expectation with respect to your current belief model over the parameterized family, and then a further expectation over the prior. But somehow those expectations are like overly like contingent on like the distribution in particular that like you chose. And so you don't have like an ability to evaluate like what if your either like parameterization is wrong or what if your prior belief is wrong, which yeah, seems to be happening a lot for me these days. So that's something called like model misspecification in Bayesian statistics. Rather than modeling that like explicitly, we said like, are there some notions that we can take from like information theory or like regularization that like might help us come up with like a different convergence criteria that like tries to resolve that? And that's where information directed sampling comes in, which was in the title. And that's like especially important for the like sparse reward setting where maybe you made some particular modeling assumption and it seems like your algorithm has converged within its parameterized family, but yeah, because you didn't catch that sparse reward, yeah, you could be kind of like overly hardened in its current beliefs, to put it in Bayesian terms. So I just want to call out, like, if we try to apply posterior sampling, this is an environment that's called the DeepMind deep sea environment, or I actually also heard it called the river run environment. It basically the Markov chain looks like a very long string with like loops going in one direction with high probability and going back to the other side in low probability. And most of the rewards are 0 except for the one near the end with the low probability. And somehow they parameterize the sparsity of this problem according to like how likely is it to transition back to the place where the higher rewarding state is. And I just want to call it like, so when this is from a 2016 Van Roy paper where they come up with this environment. I just want to point out when we take posterior sampling, let's say you could do mixture family or you could do Gaussian. But if you take that and you run it on this river run environment, you see that actually like performance degrades quite a lot as like quote like sparsity increases, or as the kind of like probability of getting towards a more rewarding state declines. Question.
I just wonder, the parameterization they used in order to make the model converge from sparse reward to the state where it has a big reward, is this algorithm of parameterization of environment applicable to any environment or just this river environment in particular?
Yeah, that's a good question. I mean, I think that like this particular notion of sparsity has to do with like how likely is it to find any rewarding state over like a trajectory. So like I feel like the inspiration for the definition maybe is broadly applicable, but like maybe the particular parameterization they have here is special to this deep sea environment. But in general, when people talk about reward sparsity, they're saying like, what is the percentage of states in which the reward is zero? Which in that sphere, I think is appropriate. That's a good question. Thanks. Right. So the point is like Bayesian regret is missing a sense of like coverage. So basically, if you took like two different policies in like a tabular environment, and one was like not exploring very much, and one is exploring a lot, there are like scenarios like this where they would have almost identical Bayesian regret. So here, like the I think the warmer, the warmer colors are the more this is a more exploratory policy, and this one is less so. This is putting more positive probability of coming to all these other states, whereas this one is relatively less. But their Bayesian regret is identical. So somehow Bayesian regret is like not suitable enough convergence criterion for like handling how well is your policy learning, or like how well is your model calibrated. So so what information so then that's where this concept of like information theoretic regret comes from, which basically they like do some like multiplication and division of Bayesian regret by the mutual information between your current policy and some kind of like oracle optimal. And that sort of like gives some new notion of like how far is your kind of like current belief from some kind of like stronger notion of oracle. But of course, they in doing this, they sort of like introduce a dependency on this like mutual information term, which is like not computable at all. So while it like works as a kind of like cute performance benchmark, we don't actually know how to like measure it experimentally unless you make some very special assumptions on the distributions. Basically, if everything is Gaussian, you can use Pinsker inequality to roughly approximate this thing with the variance, but it's not at all clear that you can. So let's go into a little bit more guts of like how information directed sampling work. Basically, in the numerator, you have vanilla Bayesian regret, but then they square it because it makes the analysis work out better. And they say, okay, let's divide it by this mutual information term, which I put it later. Hold on. Oh, yeah, I just want to point out that's just like a particular notion of like KL divergence between your current posterior and some notion of like optimal given like lowercase h trajectories. Okay, so let's go back just for a second. I just wanted that KL divergence expression to appear in the corner. Right, so information directed sampling tries to somehow like normalize your convergence criterion with the amount of information contained in like your current policy to the optimal, but you can actually evaluate the denominator. So yeah, what IDS normally does, which is in the original 2018 operations research paper and several follow-ons, is like they just say, let's just use Pinsker inequality surrogate to like replace this by variance, and that will be something that tells us all of the uncertainty in the environment. but in that way, it's somehow not truly a directed exploration because it's not like looking at like quote like distance to the target distribution sufficiently. So in general, what you would like to do is like instead of mutual information, maybe or mutual information, the idea of putting it there is roughly equivalent to putting some metric over distributions to like the target or kind of like population posterior. So what about if we replace that with like a different notion of information, which is just integral probability metric difference between current measure and target, right? So if we do that, well, then we can like apply all that we know already about kernel sign discrepancy to come up with a truly like, tractable variant of information directed sampling that that you can like run experimentally without just like squashing everything to variance. And so that's what we did in this follow one.
So previous page. So here, if you switch to your new criteria, does it still require to know the ground truth or?
No, Stein's identity helps you get rid of the. You just have to say the ground truth has some smoothness condition,
Okay.
but I don't know what that is. Actually, in later work, we figured out how to even relax that, but it gets a bit technical. So don't want to get into those guts this moment. Right. So then you can end up coming up with some new notion of like kind of Bayesian regret analysis that now what we call like information augmented. So like there are a lot of these papers from like Andreas Krauss talking about like information theoretic regret, and what they really mean is Bayesian regret, but with some additional like augmentation term. So we could come up with a sort of something that it's not tight in the horizon dependence, but it is tight in state space dependence and a number of horizons and action space cardinality. So yeah, the theory is just to show, okay, we could show that it roughly matches some prior works that do not incorporate information augmentation. That's the only point of this analysis. And to show that we could have the parameterized family be for a more general class than Gaussian. But once those things are resolved, then the rates aren't just comparable to others. So it's just broadening the assumptions, but not the sharpening the rate. Just to be humble about that part. And yeah, but then the point is like once you have this, someone talking over the Zoom.
No, that's when you talk.
Oh, okay. Oh, I got confused because it's talking to your son, but that's easy. Okay, got it. Right. So okay, so then the point is like incorporating this like information augmentation does lead to like more efficient exploration in practice and potentially like offers us a way of kind of like bridging the divide between convergence of our policy and like convergence of our like posterior model of like the reward and state representation in a way that at least prior to this work we hadn't seen. Yes, and then you can do this kind of like similar experiments with tabular environments and show that like now we are able to sort of like distinguish between low and high exploring policies according to their quote like information theoretic regrets. I think that's the only point of this slide. And yeah, just like experimentally, this like kind of like additional exploration term, which is like sort of representing uncertainty in your mixture family, does seem to like improve the like practical performance of these algorithms quite a lot. So these are for like a few different environments. This one is called wide narrow. It's called the prior MVP environment. They're also kind of like toy models, but I think like important for the purpose of like showing that like if you just did like vanilla like Bayesian like deep Q learning or vanilla Q learning, these things can be these can have almost linear regression. Okay, great. So yeah, the point is like calibrating these models is essential to efficient training in simulation. So we wanted to talk about how can we like broaden the way we're measuring convergence from simple models like Gaussians to mixture of Gaussians. How can we kind of like resolve the model's misspecification problem, which at least kind of like anecdotally or experimentally seems to have a big like point of interconnection with reward sparsity. And so we put forth some new approaches based off of integral probability metrics that are making like heavy use of Stein's identity and kernelized Stein discrepancy to like take things from Gaussians to mixture families, come up with new exploration incentives. But you know, all of these models are still sort of like not resolving the question of like access to the simulator. And like we just said, okay, well, all these model free based approaches take a long time to converge in simulator. Like, can we do can we do something that would like take less time roughly? And by the way it will take less time is that it will simultaneously like track a kind of like transition model, basically. But like in many real world applications like robotics or financial markets, we don't actually have access to a simulator that we like believe, or in another situation, like you only have access to like historically like logged trajectories. So if you only have access to this like historical data set, like what is the right way to conduct policy optimization? So I just want to spend like 5 or 10 minutes about how about some ways that we try to use these mixture family modeling to resolve this kind of like distribution mismatch issue, which is like if you have access to historically logged policies, then basically your ability to do policy evaluation in an unbiased manner goes away, because you're not able to sample according to the transition model associated with your current policy. Instead, you're only able to sample the transition model according to what's called the behavioral policy, which is like some prior collection of policies. Yeah, in finance, it's usually some like Rube Goldberg based rules-based model that has been calibrated in a very specific way for a lot of different scenarios. So in many cases, you don't even have a explicit like formula for what is that behavioral policy. You just have access to trajectories. Yeah, so I want to. So this is what we call the offline setting. Oh, I didn't mean to animate that. So in the offline, so I just want to contrast this is like the feedback loop that I had at the beginning of the talk with the woman and the canine interacting, where every time the lady provides reward feedback, and then the dog updates the policy, and then the process continues. And this assumes, of course, that you can query like a quote like world model to get access to these kind of like on policy data sets. In the like offline setting, what happens instead is this kind of evaluation stage is like happening on like a slower scale, and this data is like collected into like a quote like data buffer, and then you would like to do policy optimization given that like this data coming from this buffer is collected on a perhaps like significantly different policy than the one that this policy update is coming, needs to be evaluated on a data set which is significantly different from this policy. So in the offline setting, that different policy is called the behavioral policy. And you basically like consider that you only have access. So if you wanted to slice this just for like one particular time step and say this data buffer is frozen, and how should I like execute as many policy updates as I can just given this like data in my data buffer, that's really the offline setting. And that's saying I have a batch of data. It's coming from the occupancy measure associated with a transition model where the actions are always sampled according to a fixed behavioral policy. And what I'm really asking is like, how can I achieve some sort of a notion of suboptimality, or like what are sort of like the fundamental performance limits of this scenario. So this is like the setting of offline RL. And I just want to comment that like offline RL, like why is it hard? Well, if you just try to write out like how should Q learning work, then here's the classical Q learning update, and like there's like an expectation typically here with respect to other states and actions. And now this Q function is like evaluated on the quote like wrong data set. So instead, it's evaluated on the data set associated with the behavioral policy. At least like that's what the objective would look like for deep Q learning. And so because this is evaluated on the wrong data set, there's like this problem of what they call like Q function, like overestimation. That's pretty well documented going back 5 years now. And as a result of that, you get some like bias in the induced distribution associated with your current policy as compared with behavioral policy. And that bias like appears in sort of Q learning thinking, quote, like, I don't think that algorithms think, let's just say Q learning evaluating that its Q function is a lot better than it actually is in practice. So that's all these plots are saying. So I just want to do like a brief discussion of like what do methods for offline reinforcement learning, what do methods for offline reinforcement learning do? They try to correct this distribution mismatch between the behavioral policy and the policy associated with like what you're currently sampling from. And roughly they take a few different forms. One, like I would say the most intuitive is based off of importance sampling or like policy reweighting, where you like take the behavioral policy and its induced occupancy measure as compared with the one associated with your current policy, and you try to do, you basically use those density ratios to like reweight what you're doing. There's also, there's like a lot of different variants of that. That's what state marginal matching and variants of bootstrapping also try to do. I'll say they're kind of like hard to tune, and it's not very easy to get access to the occupancy measure associated with your, or like to get accurate estimates of these importance weights, and also they can be very high variance, I think is the big issue. So the much more like intuitive methods are based off of pessimism, which they just try to like subtract this overestimation bias. And that's what I want to get into here. So pessimism tries to deal with what they call in the literature spurious correlation, which is just like how different is the distribution from the target. So let's say this distribution is like, quote, like the true MDB transition model that you can't actually sample. And this P hat is the one associated with your offline data set. And so, yeah, typically what people do is they just say, okay, I'm going to assume under some conditions that I can replace this with a concentration bound, like Azuma-Hopding or Bernstein or whatever. And then I'll replace this like bias term with some like decreasing function of T that will like hopefully, and if I subtract that, that will like hopefully account for my bias with high probability. But, of course, that is that's only valid over kind of like a sub-Gaussian martingale noise, which I think in general we have no idea what that mismatch is actually like, or it's very hard to like justify whether it has this like unimodal structure. And in many, so here's where I want to just like quickly show, okay, we attempted to like estimate the occupancy measure or like visualize the occupancy measure of the behavioral policy of the optimal policy for a few different environments. And here we can see clear for this prior MDP, we also created like a portfolio selection environment. The occupancy measure is like clearly multimodal, or something, I would say no central tendency to be like safe. Whereas like in some of these other kind of more deterministic environments like frozen lake or deep sea, it does tend to have this behavior. And what we observed experimentally is that like for these types of environments, like your Azuma-Hopding based pessimism is sufficient. But if you have let's just say like a much more like complex structure to your distribution, then that pessimistic offset is insufficient. I think due to time, I don't want to get into too many details. I just want to like put up like what are the updates for these algorithms. Basically to point out what we eventually did is we said, let's take value iteration or Q-learning just as sort of like template algorithms for which pessimism is well established now. And there's like very kind of like rigorous studies of their sample complexity and figure out like what is the nature of mismatch for these algorithms and like when does kind of like lower confidence bound based pessimism work versus not, and what happens if we replace that with an uncertainty measure that is more calibrated to mixture family, namely one of these sign discrepancies. So that's what we did in this information directed pessimism. So here again, we're just summing over sign kernel evaluations associated with your offline data set. And so now this is coming up with like a much more fine-grained, like data-driven notion of mismatch as compared with your lower confidence bound, which is just a decreasing function of t times some constants. So we did this both in value iteration and Q-learning. And at the end of the day, what this allowed us to do is to generalize the sample complexity of a few offline reinforcement learning algorithms to the case where the distribution mismatch could have a much more like complex multimodal structure. And in particular, in some experiments that I'm running out of time to present, I'll just comment that it can lead to a significantly improved in performance, especially, so I say it's not particularly helpful in these environments where the occupancy measure has this kind of like unimodal or central tendency, but of the behavioral of the data set associated with the behavioral policy. But if you have this kind of like multimodal or like high volatility in finance terms type data sets, then you see some more market improvement. And I think with that, I probably should conclude and say I think there's like a lot of open directions here, but yeah, I'm very, very happy to take any additional questions.
Okay, any questions for our audience? Or any questions from the Zoom as well? So I have a couple of questions. So first of all, without this, so could you give us an example of how if some of these approaches or generically applied learning can be used in financial markets or in portfolio selection or something like that?
Yeah, I think that's a great question. And I would say this work was mostly completed in 2023 because you know how publications work. If it was published last year, I did it 2 years ago. Right. And since then, I've learned quite a lot, or I've gained quite a lot of knowledge about finance. And what I have to say is constructing the market simulator is very kind of like task specific. So there are things like portfolio selection, there are things like hedging, there are things like asset pricing. We naively experimented with portfolio selection here, but it's a hard problem to benchmark because you don't know what is like some notion of like optimal benchmark. And so I actually think in things like hedging, where like Black-Scholes gives you like a very nice what's called like delta hedge as the some notion of optimal solution going back to the 1973. That would like provide like a much riper scenario for like testing whether something is actually like doing well as compared to an optimal benchmark. Because I think like the question of like what is an optimal like asset allocation for a portfolio is like constantly litigated, and yeah, everyone has a different opinion about that. So you need some way of like disentangling opinion from the numbers. So I think that's one thing. I think also could be used in like asset pricing. So those are things that I like still have more to learn about, but I would think like for simulators of those tasks, it's much more promising because you do have some notion of like a ground truth like asset price or optimal portfolio hedge, whereas like in vanilla portfolio optimization, you don't. I think there's another question.
The fact that you are using deep Q learning, IDP, and other algorithm as opposed to, for example, in large language models, they mostly use PPO or GRPO, which was made by DeepSeek recently, is pertain to the difference in the distributions and the data set that you are using, that is financial market versus the large corpora of text.
Yeah, I think so. I also think like the use of PPO is widespread mostly because of the like I would say the solver has like way like fewer tunable parameters and like it's very like intuitive to use. So I think it might be an example of like its use is widespread because its use is easy, but not necessarily because it's like best for scenario A or B. Like that's just my personal opinion about that. But yeah.
The difference there is there over language model, there's no real notion of environment, right? So
Yeah, the MDP is a transition is deterministic.
so here the hard problem is genetic. Where the volatility is.
Yeah. Yeah, that is also there. Exactly. But because I think the state transition model is just token concatenation, which is a deterministic.
Yeah, so following up on the question, there is an architecture called causal transformers, which models MDPs as the transformer architecture. So uh, since it's a new model and I'm still researching on where it is going, it shows that even if there is a high database data set variance and bias, it still performs comparable to traditional Q learning algorithms. So would you have any comments?
That's interesting. I mean, causal is a loaded term. I would be like curious to understand like the particular nature of confounding that they are trying to model. Yeah, I don't know enough about how that particular architecture works. One thing I can say, just based off of like kind of reinforcement learning knowledge, is one of the things that like causality can offer is like if you have a trajectory with like high reward, mostly zeros along the way, which I think is a kind of a standard model. They have this like paradigm where you only get a reward at the end of the sentence, otherwise you don't. I think it's a textbook thing called eligibility traces, which like takes the value along that trajectory and finds some way of like weighting along at like pushing up the reward for the states that like get you along the way. And I think it would be very interesting to figure out like what is the relationship between that architecture and like eligibility traces. That's like comment number one about causality, and the other comes more from the causal inference literature, which is like they look at like conditioning variables and how to like integrate like different notions of bias and what's called that conditional average treatment effect along different confounders. Those marginal distributions, I think they look at how to do like inverse weighting based off of those probabilities. They call it marginal importance, marginal inverse propensity scoring. So I'm just like wondering what like how did they come up with this causal transformer?
So
And like how is it like incorporating kind of like best practice for kind of like deconfounding or sequence modeling in like RL or
the causal architecture, it creates a token, like a tokens list or a token set of states, actions, and rewards, and plugs it into the transformer and generates the next action as the new token.
I see. No, I know, but like it needs, but how exactly it's coming up with the sequence model, how it's doing the weighting, I would say needs to be related to some trying to do some sort of trajectory decomposition of the reward. Yeah, I don't know. We can talk offline. I think that's more to discuss. Yeah, very interesting.
Excuse me, can I ask a question?
Yep.
So when you do sampling, what is the output? Is it the action? You sample an MDT? Not clear for
And you
me.
get a new you're talking about in the information directed sampling. Yeah.
You had a slide that there was a fee in the first maybe 10 slides. I don't know the number.
Let's go way back. Actually, let's just go to the let's go to the pseudo code. Maybe you're asking about how this works.
Actually, there was a fee that was
You
modeled
used
in your
earlier.
distribution. I think that
Oh, I
distribution
think
was
the
like the
fee
first
is even just the prior over your transition model. Something like that.
Who's the next line? Pass. Here.
Oh, yeah, exactly. The fee is just like putting a prior over your rewards and your state transition model.
This is being modeled later at a mixture of Gaussians or what?
Yeah, say at time zero, this is a zero, like a zero or a single Gaussian, and then you come up with like a way of adding new Gaussians in a recursive manner.
And why a mixture of Gaussian is a good model for reinforcement learning?
I think that's a fair question. We came to it thinking, well, if people try to make posterior sampling work for MDP and continuous space, currently the standard for which there's any theory is single Gaussian. So in the spirit of baby steps, but not in the spirit of this is the best possible thing to do.
Thank you. Yeah. The reason I asked that question is that because you cannot say like a state is close to the other one just using a Gaussian, right?
Yeah,
Because states can be complex, can be an image. You cannot say how they
Yeah.
they're close.
exactly.
Or yeah, probably you should lift your data to a space that the states are more meaningful in terms of Euclidean distance, right? When embedding space that embedding space, then you can use mixture of Gaussian, probably.
Yeah, exactly. That makes sense.
Thank you, everyone. Nice, very nice talk. The second speaker